simple, few reactions only, primarily used for synthesis. So we study Grignard and organolithium compounds. So the key thing about these two compounds, these two reagents is that, remember, by means, so what is an organometallic compound? It's a metal bonded to a carbon, right? So we can make a Grignard from a bromoalkane or any haloalkane by doing the reaction with magnesium in ether. Ether is a solvent. And by doing so, what we are doing is inserting the magnesium in between the carbon and the bromine. And what happens with that, as you guys know, is that now magnesium is way less electronegative than carbon. So the big deal about organometallic compounds, especially organolithium and Grignard, is that we are turning the haloalkane, which is quite, remember, the carbon in the haloalkane is quite electrophilic, right? Because the bromine is more electronegative. Whereas in the organometallic compounds, now what is bonded to the carbon is the magnesium or lithium. And in that case, the carbon is more electronegative. So that leads to a very strong Lewis base or nucleophile. Okay, so that's the big difference between organometallic compounds, and that's why they are so relevant. So I'm going to emphasize here the bond polarity. This is a big deal. And I said, so what's important about this, in addition to this, is for you to know that these two are very, very strong Lewis bases. They are even stronger than sodium amide, okay? Because of these guys. And this is what somebody asked before. I'm going to repeat it right now. You can only use Grignard and organometallic compounds for ring opening reactions of epoxides or carbonyl compounds. Carbonyl compounds, we are not discussing them in this class. So only used to ring opening reactions of epoxides and addition to carbonyl compounds, not discussed in the class. So only the first part is what we learn in class. You can never ever use Grignard, and I'm gonna write it over here again, so it's written. Hopefully, you guys won't forget about this. Can never be used for nucleophilic substitution reactions. They always produce only elimination. So please don't react, do not react them with haloalkanes. Okay? Never and
I
never.
also want to clarify, so they don't show up in the product. They're more like a catalyst to opening the ring, correct? Or do
No,
they
they do.
show?
They form a carbon bond with the product. Yeah, I'll show now. So this is about these two. Um, the one thing that extra thing that we learned with this was we also discussed the Gilman reagent, which is basically organocopper reagent. So is from a lithium organolithium compound, you can make a Gilman reagent. In that case, um, the compound, so the carbon, it ends up bonded to a copper, and you end up with two alkyl chains bonded to the copper. So difference between uh, Gilman and organolithium, that you can certainly use Gilman for nucleophilic substitution reactions. I'm gonna just give you an example, and this is the big difference between the three of them. So once again, you only use Grignard and organolithium for epoxide ring opening reactions. You can use Gilman for nucleophilic substitution reactions. Okay. So that's the difference between the three of them. And the main use that we had for these two guys, the Grignard and organolithium, was for epoxide ring opening reactions. Remember, we can make epoxides very easily from alkenes with NCPVA. That reaction is also stereospecific because the stereochemistry of the epoxide depends on the stereochemistry of the alkene. So once we get the epoxide, you can open an epoxide with an organolithium, always in the lower substituted carbon, as I just discussed a few minutes ago. So if you use, for example, let's say this organomagnesium compound to open this epoxide ring. So now the carbon is nucleophilic. So we have 1, 2, 3, 4. We are connecting this carbon with this carbon over here. So I'm gonna just track. As I said in class, guys, I suggest you guys to number the carbons. So we have 1, 2, 3 in the epoxide. So second, here's gonna be hydroxyl. Keep track of stereochemistry as well. If you got a racemic mixture, which is gonna happen here, the racemic mixture is gonna be carried over to the following reaction, obviously. So keep that in mind. So give me 1 second. So I'm trying to look for the symbol for the racemic mixture here on the program. Hopefully I find it soon. I can't find it, but anyways, I have a racemic mixture here. I'm gonna write racemic list. But you're gonna keep carrying over to the next step. So here we have the second carbon is a, let me fix this. This is, so if you open this, obviously you're gonna get an alkoxide here. So please correct that, make sure that this is corrected. And then we are bonding this carbon here to this carbon here. So this is carbon 3, 1, 2, 3. We're making this bond. So I'm gonna color code this so you guys can track of what's the bonding that is happening. And then we have 1, 2, 3, 4 carbons, 1, 2, 3, 4. So that is correct. So we're gonna continue with a racemic mixture here in the product. And then we can do hydrolysis here to record the alcohol. So you can use organolithium, you can use a Grignard, you can use a Gilman to open an epoxide. The result of opening an epoxide is you're connecting two carbons that are sp3, and you're getting, in addition to that, a hydroxyl functional group. So for synthesis purposes, this reaction is quite useful. Okay. So in summary, for organometallic compounds, we study Grignard and organolithium. These two can be used to open epoxide rings at the lowest substituted carbon that allows also to not only connect two carbons, very important carbon-carbon bond forming reaction, but in addition, you get an extra functional group, an alcohol. From the organolithium, you can make a Grignard, a Gilman reagent with copper iodide. And the Gilman reagent is the only reagent that we can use to make a nucleophilic substitution reaction. So that's quite handy too. So that's very important for synthesis purposes. Keep that in mind. And then, yeah, I gave you problems for you guys to practice. Is there any question in regards to organometallic compounds? No questions?
No, I just want a summary. So we only use Grignard to open an epoxide or
Grignard
create.
and organolithium just only for epoxides. Gilman
Yes.
can be used for epoxides and is the only one that can be used for nucleophilic substitution like here.
Chain. So okay, thank you.
Any other questions?
Yes, so Gilman would do SN1 or SN2 substitution. Which
It's
one?
an SN2 like reaction, no carbocations in Gilman.
Okay.
Mm-hmm.
And the electrons flow from the carbon that is a nucleophile, right?
Mm-hmm. The carbon is still more electronegative than copper.
I see.
All right,
Professor,
guys. So go ahead. Mm-hmm.
since you said Gilman can also open epoxide rings in our synthesis problems, can we just use Gilman for all of our carbon-carbon bonds?
You could, but you're gonna need to know organolithium and Grignard in organic too. Okay, so if you choose to ignore them now, it's not gonna be pretty for next semester.
Okay, thank you.
Mm-hmm. So when will I use Grignard or organolithium to open an epoxide? In any synthesis problem where I need to extend the carbon chain and a hydroxy group. So when you see a synthesis problem where extending the carbon chain is one goal and getting an extra hydroxy group is another one, most likely you're gonna have to open an epoxide with a Grignard or an organolithium.